Okay, first thing, there's a problem like this on the homework for 5-5. So you want to fill in the blanks to create 4 isosceles triangles. If it's impossible to build an isosceles triangle, you put NA in the boxes. So we'll just write in here what we put in the boxes in Moodle. So if you're given a 24-inch piece of wire and you want to bend the wire to create an isosceles triangle from the wire, so that each side of the triangle is a whole number of inches, okay? So what would we do here? Somebody raise your hand and help me out here. What would we do with this first case, where I know that one of the legs is 7? Okay, what's the other leg going to be then, for sure? 7. If it works, it'd be 7. This would be 7, right? And then, so those add to 14. If I subtract that from 24, it leaves how much for the last side, which is the base? 10. Okay? Is that a possible triangle? It is, isn't it? Right? How do you know it's a possible triangle?
Because 7 is greater than 10.
Okay, right, because no matter which two sides we pick, the sum of any two sides will always be greater than the third side, right? And really, the only one you have to check, if you can see the sides of all 3, is check the smallest 2. Do the smallest 2 add to something bigger than the largest side, the longest side of the triangle? 7 plus 7 is greater than 10, so it works. Okay, what about this guy right here? What if we don't know what either one of the legs are, but the base is 14?
You are not able to create it.
Okay, I subtract 14 from 24, and I get 10 left over for both of the legs. So what would they have to be?
5.
They'd have to be 5. Okay, does that work?
Yeah.
Some yeses and some no's.
So you put NA in each.
How come it wouldn't work, somebody?
Because 5 and 5.
Here, go ahead.
5 and 5 plus.
Yeah, 5 plus 5 is not greater than 14, so that can't work. Good. So this would be a case where we would have to put in NA, because it can't work. What about this guy? What if the base is 8? That leaves us how much for the 2 legs?
8 on each.
16 total, 8 on each. So can that work?
Yeah.
Well, obviously, yeah, right, because they're all the same length. Okay. What if one leg is 11? Let's make the other leg 11. How much is left over for the base? 24 total. So that adds to 22. So how much is left for the base then? 2. Does that work? It actually does, doesn't it? Because obviously 11 plus 11 is bigger than 2. But 11 plus 2 is also bigger than 11, right? So yeah, that one works. What's that? Whatever that noise is, let's not do that. It's distracting. Okay. Oops. There we go. Okay, here's another one that was asked about. Now, I made it harder than the one in the book. The one in the book was kind of dorky. They just said if show an inequality that says specifically one side is bigger than the other two. But I want you to do more than that. I want you to solve for all the possible values of x. And so what you're going to end up getting is some kind of a compound inequality. What I want to see coming out of this is, for your answer, something like this. X is greater than something and less than something. So what are the possible values that x could have that would make that into a triangle? So how are we going to do that? Let me ask you this. What could make it not work? What could make x not work? Okay, if the sides don't work. If 2 of the sides don't add up to a greater number than the other side, right? So we'd have to just take all 3 cases and see what each combination, what kind of restrictions that it imposes on x. So let's take, I'm going to color code these, how about? We're going to have red, blue, and green, how about? So we could say red plus blue has to be greater than green, right? Okay. So x plus 2 plus 3x minus 1 has to be greater than plus 4, right? So what's that going to do for us if we solve this? We'll do some algebra. So on the left side, if I combine all the like terms, what do I get? Okay, yeah, x plus 3x is 4x, 2 minus 1 is plus 1, is greater than x plus 4. So which side do we collect the x's on? Well, on the left side, because we want a positive number of x's, right? So we'll subtract x from both sides of the inequality, and I'll push the numbers the other way, right? So I'll subtract 1. And I get, what, 3x is greater than 3. So therefore, what's the last step? Okay, divide by 3, so then I would just get x is greater than 1. Make sense? Okay, so there's one result. That's the result I got from this case. Now let's look at another one. Let's go over here and let's try. We said red plus blue is greater than green. What if we did red plus green is greater than blue? So x plus 2 plus x plus 4 is greater than 3x minus 1. Okay, let's do the algebra. So on the left side, if I combine like terms, x plus x, whoops. Two x plus 6 is greater than 3x minus, is this supposed to be a 1? Okay, which side am I going to collect the x's on this time? Right side? Okay, so subtract 2x from both sides, which means I want the numbers on the other side, so I'll add 1 to both sides. And I get 7 on the left and x on the right. So 7 is greater than x. Another way of saying that would just be x is less than 7. Right? Okay, last possibility. Last possibility, what didn't we do? I guess we didn't do blue plus green is greater than red. Okay, so we can do, oops. 3x minus 1 plus x plus 4 is greater than x plus 2. Okay, let's scoot down and we'll solve that one. Okay, so if we solve that, combine like terms on the left side and get what? How many x's? On the left side? 4x. Negative 1 plus 4 plus 3 is greater than x plus 2. So collect x's on the left, right? So we'll subtract x from both sides, subtract 3 from both sides. And I get 3x is greater than negative 1, right? So those cancel. And then divide by 3, right? So x is greater than negative 1/3. So those are the three. Now let's look at these three restrictions, because I can only pick the values of x that survive all three of those at the same time, and meet all three of those restrictions simultaneously. So let's see, our numbers are x is greater than 1, x is greater than negative 1/3, and x is less than 7. Well, this one, does it make sense that this one right here has to survive because it's the only upper constraint? Right, it's telling us x, the only one that says x is less than something. But both of these guys over here are saying x is greater than some smaller value. Well, which is the only one of those two that will work in both cases? In other words, are all numbers greater than 1 also greater than negative 3, negative 1/3? Yes, but are all numbers greater than negative 1/3 also greater than 1? No. So we got to toss that one, right? So we end up with these two statements are the ones that we use. So if I write those in the form that we want them, like this, x is greater than some lower value and less than some upper value, doesn't that just look like x is greater than 1 and less than 7? So that gives us the range of values that x could be, right? Anything between 1 and 7 would work. Anything else would not work. Okay? Make sense?
Yeah.
Okay. All right, so just very, very briefly, like I say, I really don't want to spend a lot of time on this, but let's take a quick look at 5.6. There's something on this that's kind of interesting. I think you'll like. There's really two parts to this: indirect proof, and they talk about the Hinge theorem. So there's really just two things we want to focus on. Use the Hinge theorem and its converse to compare sides in a triangle, and then indirect proof. Now, let me just summarize this. What indirect proof does, the proof that you guys have all done, is what we call direct proof. And you don't need to worry about all these fancy words, but direct proof just says I'm going to go through a list of statements that shows how if I start here, I have to end up down here. Indirect proof is completely different. Indirect proof is really effective, it's really simple to use, and it works a lot outside of math too. What indirect proof does is instead, we're going to assume that what we're trying to prove is false. And then we'll just, by assuming that it's false, we'll look at what the conclusions are that we can draw from that until we run into one that we know can't be true. And then if we run into a result of our assumption that doesn't work, we know that our assumption had to be wrong. Okay, and so we can actually prove something that way. The Latin name for this is reductio ad absurdum, which just means solving by absurdity, by logical absurdity, showing that your assumption is absurd and you can't work. Okay, so before we do a geometry one, let's just look at kind of something that's maybe just a regular life one. What if we said, for example, let's say I said that I drove, I don't know what's 90 miles away, but I drove to some city that's 90 miles away, and I got there in an hour. But did you speed? No, I never went faster than 60, I said. Okay, so that doesn't sound right, does it? Right? Okay. No, I didn't though. I went 90 miles. So how could we show really quickly, logically, that that's an impossibility? Well, that's kind of the idea, right? So we could do something like this. We could say, well, let's use an indirect proof and say, okay, I went 90 miles in an hour, but let's just say I did not go faster than 60. That's what I'm saying. What you're going to try to prove is that I did go faster than 60. Right? So we'll make the assumption that I didn't go faster than 60, that I only went 60. So we could just say, okay, that's fine. Let's follow that assumption and see where it takes us. If I really did go 60 miles an hour, how long would it take me to go 90 miles? That'd take me an hour and a half, right? And so if I left at 9:30, I'm saying I left at 9:30 and then I got there at 10:30, that's impossible. Because if I left at 9:30 and I was truly going 60 miles an hour, I wouldn't get there until an hour and a half later, so it'd be 11 o'clock, right? And so there's my contradiction. Because by making the assumption that I never went faster than 60, in fact, we just assumed that I went 60, the conclusion that we drew from that was that I would get there at the wrong time. And so therefore we showed that we proved it. I had to go faster than 60 because by assuming that I went 60, it didn't work. We came to some absurd conclusion that wasn't right. What if, let's say we're in here where we can't see any, there's no windows or anything, right? And somebody shouldn't be doing this, but they looked on a smartphone and said, oh, smartphone says it's what are you going to say? Hang on. Let me think about this for a second. They could say, it's raining outside. Okay? And we can say, how could we prove that it's raining outside? Well, we could, I assume, and that's blocked off. Yeah, we can't look up there. That'd be nice and easy, huh? Okay, so, no skylight. So if, we could say, okay, well, let's assume the opposite. Let's make the assumption that it is not raining outside. Okay, if it's not raining outside, what conclusions could we draw from that? Could we draw a conclusion that we could show is incorrect?
The ground is
But we can't see outside, but people walking into the room maybe, if it were dry outside, what would they all have in common as they walk into the room? They should be dry. Yeah, they should be dry. Okay? So all it would take is for us to see someone walking in the room with their coat on, and the coat was all wet, and then we could say, aha, that violates, that doesn't work. Because if it were, we made the assumption that it's not raining. If it's not raining, everyone walking in should be dry, right? So if we can see somebody that's not dry, then we just prove that it must be raining by indirect proof. Does that make sense? Okay, so let's take a look at one geometry example. And in a way, it's kind of nice to do some that aren't geometry, but the geometry ones are just they're so easy to do because the rules are so, we all know the rules. And it's just really cut and dry. So let's say here, given some triangle ABC, we want to prove that triangle ABC does not have more than one obtuse angle, I should say. Not triangle. Does not have more than one obtuse angle. Okay? So if we're going to do an indirect proof, what assumption would we make? That it does have more than one obtuse angle, right? So let's see where that takes us if we make that assumption. Okay, well, if we assume that it does have more than one obtuse angle, let's say that A and B, for example, that A is greater than 90 and B is greater than 90. Well, if those are both greater than 90, then what is the measure of A plus the measure of B necessarily have to be greater than? If I add those up. Yeah, if the measure of A is greater than 90 and the measure of B is greater than 90, then their sum must be greater than 180, right? That's our logical conclusion from that, okay. But we know some stuff about triangles. We know that all three angles have to add to 180, don't we? So we could say the measure of A plus the measure of angle B plus the measure of angle C is equal to 180 degrees, right? And then from that, we could say if I just subtract, do a little algebra, subtract the measure of angle C from both sides of this equation, I also conclude that the measure of angle A plus the measure of angle B is equal to 180 degrees minus the measure of angle C. So now I've got two conclusions that I've drawn about the measure of A plus the measure of B. From our absurd or indirect or our opposite assumption that there are two obtuse angles, we got that the measure of angle A plus the measure of angle B is greater than 180. But from the triangle sum theorem, which we know that A plus B equals 180 minus C, right? So what if I just substitute and see what happens? What if I take this stuff, because A plus B equals 180 minus C, and I plug that in right there. Well, then I get the conclusion that 180 degrees minus the measure of angle C is greater than 180 degrees. If I just subtract 180 from both sides, I get the result then that, or let's do this. Let's go ahead and add the measure of C to this side. I'm going to write this down. I'm going to write this down. So hang on. We're going to be, here's what we've got. I don't like the way they did that. So here's the statement that we have. We said 180 degrees minus the measure of angle C equal, or is greater than, sorry, greater than 180 degrees. So let's add the measure of angle C to both sides. Okay, so that's going to give me 180 degrees is greater than 180 degrees plus the measure of angle C. It's starting to look a little crazy, isn't it? If I subtract 180 from both sides, I get 0 is greater than the measure of angle C. Or another way of saying that, the measure of angle C is less than 0 degrees. Is that possible in a triangle? No, that's absurd. That can't happen. And so therefore, our assumption had to be wrong. more than one obtuse angle in a triangle, because if there are, this is the result. See how that works? That's pretty slick. Okay. All right, and then the other thing I'll just really quickly show you, and I'll make this brief. We'll come back to this a little more later, too. But the Hinge theorem. Hinge theorem is really simple stuff. I guess let's summarize. The last statement is not possible, and so therefore we can conclude that our assumption is false. So if you want to look at some guidelines for an indirect proof before we jump onto the Hinge theorem, identify the statement you want to prove is true. Begin by assuming the opposite. Assume that it's false. Okay, its opposite is true. And then obtain statements that logically follow from your assumptions. In other words, what can we conclude from that until we obtain a contradiction? One of the conclusions of our assumption is wrong, and then that's the proof. And we know that our assumption must have been wrong, and therefore has to be true. Okay, the Hinge theorem. This is all the Hinge theorem is, and the name is very descriptive. In two triangles, take these two triangles, look what happens if we know that I've got two pairs of congruent sides in two different triangles. So in this case, side AB we can see is congruent to side, what is that, D something, I can't see what that's supposed to be. D, whoops, I don't know, I'll make it the letter. What did it have to be, an E? Can you see it? Well, it's got to be an E, right? So this guy down here is an E. So AB is congruent to DE, and BC is congruent to FE, right? If the included angle between those two congruent sides in the first triangle is greater than the included angle in the second triangle, what does that tell you about the third sides? You can kind of see it from the picture. What does that tell you? And I think a good analogy here to think about is, what if the congruent sides, just pretend those are like sticks maybe, right, that are the same length, and they're hinged, hence the name, the Hinge theorem. They're hinged in the middle, and then the third side is a rubber band that can stretch or shrink, right? So I got the same length sticks that are hinged. So same length sticks that are hinged, and here's my hinge in this triangle, right? And then I've got my rubber band. Okay. Well, if the hinge is open to a bigger angle, right? If the included angle, meaning the hinge angle, is bigger in one triangle, what does that tell you for sure about the rubber band? What conclusion could you draw? As the hinge opens up, what happens? It's stretched. That has to be. So that's all the Hinge theorem says. It seems like it's why you make a theorem out of it, but it is useful. So if I have two pairs of congruent sides, when the included angle is larger, then that means the third side in that triangle has to be bigger. Okay? We know that big angles go with big sides, right? Okay, and then there's a converse to that too that works. We can say it backwards. We can say, if I know that I've got two triangles with two pairs of congruent sides, and I know that, let's say, the third side of one triangle is larger than the third side of the other triangle, then doesn't that mean that if the rubber band is stretched more, the angle must be bigger? So there's the converse. Okay. Two pairs of congruent sides, if the third side is bigger, then the included angle is bigger. Okay? And so the kinds of things you can do with that you'll be doing on the assignment, real quick example, I'll just let you look at one. We'll prove it. Possible side length. So if we said something like, let's say that we knew AB was congruent to DE and BC was congruent to EF, and let's say we knew that AC had a length of 12, and the measure of angle B was 36 degrees, the measure of angle E was 80 degrees, what could you tell me about the length of DF? Which of these possible lengths would work? 8, 10, 12, or 23? What do you know about DE compared to AC? If this angle is bigger than this angle, but the hinge side, the sides of the hinge, right? Look at these congruences. That's congruent to that. That's congruent to that. So what do you know? If the hinge angle is 80 degrees here and 36 degrees here, what's that tell you about the rubber band? Stretched more, right? It's got to be bigger. So I know that this side right here, DF, has to be greater than 12. There's only one possibility that's greater than 12, and it's 23, right? So that's got to be the answer. That's the kind of stuff we do. Okay, no big deal. I think I'll call it quits when we get down there. That'll get you started. You know, I'll answer some more questions about that later.